Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 8-4 lesson on conversion and convergence. In this one, we're going to convert between power series and rational functions, and we'll figure out how to get the interval of convergence for an infinite geometric series. For the warm-up, we're going to start with a familiar problem type. Here's an infinite series. See if you can figure out whether this converges or diverges to the best of your ability. And if it does converge, give it sum. Alright, so the key on this one is recognizing that this is a geometric series. We're multiplying by something over and over again. Since it's geometric, we need to know the a1 value and the r value. For a1, we've just got our initial term here, 1. And then for the r value, that's what we're multiplying by each time. That's just x. Now here's where things get a little bit interesting. The absolute value of x, is that less than 1? Well, we don't really know. That depends on what x is. So this is going to converge at the very least if x is a number between -1 and +1. It's going to diverge if x is 1 or greater. So we have to assume, if we're going to find the sum, that x is between -1 and 1. So given that assumption, x is between -1 and 1, what's the sum of this going to be? Well, that's just going to be a1 over 1 minus r, which in this case is going to be 1 over 1 minus our r value of x. But now this is true only if x is between -1 and 1. If x is not between those, then this is just a garbage value. So there are two things that come out of this whole warm-up here. The first is that we can convert back and forth between an infinite geometric series like this one and a rational function. This is just a plain old rational function, 1 over 1 minus x. The other thing that comes out of this is that we need to talk about an interval of convergence. So these are x values where your series and your function are equivalent. And if you're within those x values, then the series and the function converge. If you're outside, then all bets are off. Before we go any further with this lesson, this is the why do we care part of the lesson. Why do we care about converting between rational functions and geometric functions? And why do we care about interval of convergence? So to demonstrate all of this, I made a little Desmos slider for you to play with. Basically what happens in this slider, and here's what the left side of the page is going to look like when you go to this website. You basically got this rational function that we just found in our warm-up, and here's the series that you can use to turn into this rational function. It turns out when you have a polynomial, you can use it to model different types of functions. And the longer your polynomial is, the more terms this series has. As you have a higher and higher k value, the better your polynomial is going to model the original function. So if we actually go to this Desmos site now, the blue line here is the polynomial that we're using to try and model our rational function. The red line's the rational function. We can see that when we have a series with a k value of 0, we've just got the line y equals 1, and it's not a very good model of the rational function. But as we make the k value bigger and bigger and bigger, we see that our polynomial, as we add more and more terms to it, starts to model the rational function a little bit better. Pause the video and play around with the slider and see how well you can make the series model the original function. Alright, so you probably noticed something interesting doing this. As we make this k value higher and higher and higher, adding more terms to our polynomial, we see that we're actually not getting much further than this -1 here, or +1 for that matter, in terms of how the blue line and the red line match up. And if you make this go all the way out, so let's just kind of zoom forward a little bit. If we make this go all the way to k to the 30th, we haven't really gotten any better of a model. We're kind of stuck between -1 and +1. So just to show you a little recap in my PowerPoint slide now. So we had the k values. I'll just look at 0, 1, 2, 3, 10, and 30 just to get a kind of a few snapshots. So here was k equals 0, k equals 1, k equals 2. As we're adding more and more, we're modeling better and better. Here was k equals 3. 10 didn't really do much more for us. 30 really didn't do much more for us. We're seeing that the model is kind of stuck between -1 and 1. Now the reason for this is, and we just found this before, our series converges only between -1 and 1. Those are the values where the infinite geometric series actually gives you a real value when you do that infinite sum formula versus some kind of far-off garbage value. So now that we've seen that lovely eye-opener on Desmos, we're going to take a look at converting from a series to a function. So for here, we want to find the interval of convergence for this thing and the function of f or x represented by this geometric series. Let's start by getting the a1 value and the r value for this geometric series. Pause the video and get that. All right, so for the a1 value, we had 3. For the r value, 12x divided by 3 is 4x. And you'll notice we just keep multiplying by 4x over and over again. So now to get the interval of convergence, you're just going to take your ratio, your common ratio, put it inside the absolute value, and force that to be less than 1. So we're just going to start with absolute value of r less than 1, and then we're just going to solve that inequality. So we've got absolute value of 4x less than 1. And now let's see if you remember how to solve an inequality with an absolute value in it. Pause the video and give that a shot if you remember. All right, now if you don't remember, there's a few ways to start this. You could actually divide by 4 right off the bat, or you could set up one of those double inequalities. So do -1 less than 4x less than 1. And now, at this point, if whatever you do to this x in the middle, you have to do to these other two numbers as well. So to get x by itself, we're just going to divide everything by 4. So we can say -1/4 less than x less than 1/4. So our interval of convergence is between negative and positive 1/4. Now to get the function of x, all you have to do here is just take the sum of this series like we did in the warm-up. Pause the video and do that. So again, the series sum formula, that's a1 over 1 minus r. So that's really just going to be 3 over 1 minus 4x. Simplify if you can. There isn't much to do simplifying here, so this one's actually done. But again, this function and this series really only match up between negative and positive 1/4. We're going to do another one of these examples where you're converting to a function. So pause the video and see how far you can get on this one. All right, so for a1, since this is an infinite geometric series, for a1, we've got 0, the lower limit of summation, being plugged in for n. So that's all just going to come out to 1. For the r value, it's whatever is being exponentiated, repeated over and over with multiplication, so 2x minus 5 again. And for the interval of convergence, we've got absolute value of 2x minus 5 less than 1, which means that we can write -1 less than 2x minus 5 less than positive 1. So now we have two steps to do here. We have to add 5 and divide by 2. So adding 5 everywhere, we've got 4 less than 2x less than 6. And now dividing everything by 2, we've got 2 less than x less than 3. So there's our interval of convergence. Now to write it as a function, we're going to do the a1 value over 1 minus this r value of 2x minus 5. And we're going to do that inside of parentheses. And just to simplify this, this is really 1 minus 2x plus 6. So we can just write, or plus 5 rather, so we can just write 6 minus 2x for the final answer on this one. For this next problem, we're going to go the other direction and turn a function into a power series. Specifically, they want us to write the first 4 terms and general term of a power series, and then identify the interval of convergence. So we're going to start by getting the a1 and the r value for this. Pause the video and see if you can figure those out. All right, now it helps if you've got a1 over 1 minus r written out somewhere so you can just match the forms. If you look at the form, you'll see that a1 is just whatever's in the numerator, 7x in this case, and then r is whatever is being subtracted from 1. So in this case, that's going to be positive 3x because it goes 1 minus r. Next, we're going to write out the first 4 terms of the series. To do this, we're going to start with a1. We know that's the first term of the series. So I'm going to write f of x equals 7x. And then I'm going to have to add some more things here. To get each additional term, well, this is a geometric series, so I'm just multiplying by r to get the other terms. So we've got 3x times 7x, that's 21x squared. And then pause the video and see if you can get the next 2 terms. All right, so 21x squared times 3x is 63x cubed. And then we'll have 189x to the 4th. And now we have to deal with the general term. So I'm going to write plus dot 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 plus, and we'll talk about the general term now. So for this general term, we're essentially just asking for the summand from sigma form. So if you were to convert this series here into sigma form, what would you put for your summand? And You need to kind of know the initial n value when you write sigma form, but for this you can actually use any n value you want, some initial n value, but I usually use 0 just to be on the safe side. So just let's use 0 for this one. Pause the video and see if you can come up with a general term for this series. All right, so we have a 7 to start with, and that keeps getting multiplied by a 3. I'm going to put 3 to the n, because if n is 0 to start with, that means we've really just got 7 times 1 for that first term. I also need an x in there, and for my exponent on this one, I'm going to put x to the n plus 1. The first term has an x, so if 0 is my first n value, that means I need x to the 0 plus 1 to get this x in here. And let's just double check and make sure that works on the second term. So if n equals 0 gave us this first term, n equals 1 would give us the next term. That would be 7 times 3 to the 1, which is 21, times x to the 1 plus 1, which is x squared. So that works. So with general terms, don't freak out about these. Just try something out, see if it gives you the first two terms, and if it doesn't, change it a little bit. There is one other important thing we need here. I'm going to need to write a plus ... here because this is an infinite series. So if I just stop with this term, I'm saying it's not an infinite series. And now finally for the interval of convergence, we've got our r value here, absolute value of that less than 1. So we've got -1 less than 3x less than 1. And now to get x by itself, we're just going to divide everything by 3. So -1/3 less than x less than 1/3. Just for practice, we'll do one more of these. Pause the video and see if you can convert this into 4 terms in a general term with interval of convergence. All right, so we have an a1 value of 1/5. Our value is going to now be -x/5 because it's really 1 minus r here. So for our first term, we've got just 1/5. And now we're going to multiply by -x/5 each time. So our next term will be -x/25 plus x squared over 125 minus x cubed over 625 plus ... And now we have to figure out that tricky general term. Now, since this is an alternating series, since it goes back and forth, plus, minus, I'm going to put a -1 to the n as part of my general term. And I want to make sure the first term is positive here. So if I make this n and my n value is secretly 0, that'll give me a positive to start with here. Now, something else I notice in each of these terms, I'm always thinking about constants and x's. So for my constants, I've got a 1/5. This is essentially kind of a 1 over 25. So I've got this 1/5 kind of getting multiplied throughout here. So I need a 1/5 to some power. I want the first term to have a 1/5 in it. So if 0 is my first n value, I need to make this 1/5 to the n plus 1. So if I plug 0 in for n, I'm going to get 1/5 to the 1 for that first term. And then the next term will give me 1/5 to the 2, which will give me this 1 over 25 action that I want. Finally, I need the x. Now, since the first term does not have an x in it, I want x to the 0 to be my first x. So I'm going to write this here as x to the n. And then again, don't forget the plus ... because it's an infinite series. Finally, for the interval of convergence, we'll let our r value be less than 0, absolute value of -x/5. Now, you might be wondering, what exactly do you do if there's a negative in here? The nice thing is, if this whole inner thing is being multiplied by a negative, absolute value, you can just make that positive. So I'm just going to write this as -1 less than +x/5 less than 1. And that is equivalent to what we have here. So now we just have to multiply by 5 on each side. This will be -5 less than x less than 5. And that is it for our series on sequences and series. Till next time, Mr. Sutton signing off.